I'm going to be talking about subnetting. For people out there who are struggling with TCP/IP and trying to get the subnetting process down, this is really aimed for you. I'm not going to go into a lot of details about all the nuances of TCP/IP because you can get that out of a book. I'm going to hit subnetting because most people struggle with this process. I've seen presentations that are, some of them try to explain TCP/IP, but I think many times it's not. It's made more complicated than it needs to be. Also, some people just try to teach you the charts and the ways to memorize charts, and that doesn't teach you TCP/IP subnetting. I think if you're going to be an IT on a system side, or especially a networking side, you got to understand this. Otherwise, you're always going to have problems. So I have a 6-step approach that I use. How many subnets do you need? I know that in most cases you're going to have somebody ask you to add X number of computers. But if you follow this process, you'll see that each answer feeds the next question. If you did it down, you can start at any spot, do it frontwards, sideways, backwards. It won't matter. It's mostly the process because it's just the way it lends itself to each question's answer feeds the next one down. So I go with this angle. I've taught this to students in the past when I was teaching, and they found it helpful, so I throw it out there on the internet, and hopefully this is helpful to you too. I'm going to use an example. We're going to have to hunt down Alfred E. Newman in the 3D world in the real environment, just so that you can kind of get an idea of how what subnetting really does. So let's say I got to go to 208 Mad Street, Building 2, Suite 172. I would find Alfred if I had to find him by driving to a business park, which is nothing more than a network of buildings, and then I might go to Building 2, which I've kind of picked out of here arbitrarily, and that would be a network of offices, and then I would go to Suite 172 down here, which is nothing more than a network of cubes, until I found Alfred down here at the end in Cube 5. So that's really kind of how TCP/IP works, but we can't put walls up. We have to use this binary and use a linear 32 bits. So if this was a business park, 208 would be here, being the least specific, and then you get more specific until you finally get down to Cube 5. And you would know that these are networks because the mask, which shows 255.255.255.0, separates the networks from the computers. That's all it does. It just simply tells you where the networks stop until you get to the host, and that's what you're looking for. So this is a way of passing through networks until you get to where you're going. So let's say we're going to subnet Albert's office. We're going to, in the real world we would put up a wall, which I'd take a little blue wall here. But in the digital world, if we were to subnet a network, it would be a 0 network or a 128 network if we were going to have 2 subnets. And while it makes sense seeing a wall, it's another thing trying to understand how we came up with 0 and 128. So that's the process I'm going to take you through. Okay, so if I were doing the business park analogy again, notice everything's the same here except the mask. 128 is what we've changed to. And looking at Albert's computer 5, you can tell that he's in the 0 network because it's below 128. But that doesn't tell you how you get to 128 and why that is the number that it is. So you really, in order to understand this, have to look at it in binary. You have to understand what's happening in the binary level. So down here, computers look at the full 32 bits. They don't look at this dotted decimal notation. That's for our viewing pleasures because it's easy for us to work with 3 numbers at a time, and we can memorize those numbers easier than saying some astronomical number in the billions. So what we do is we simply type in these numbers, and at the binary level, this is what's happening under the hood. This 128, 64, 32, 16, 8, 4, 2, 1 is simply a template for placeholders for each 8 bits. Collectively, they add up to some large number. This is the 128 bit that we're turning on, and that's why we put the number 128 in this box. So the 128 mark has been turned on, 128 goes into the box, and it says I'm in the 128 network, and it's sort of a strange environment. You're telling the computer when you write the number 5, that you're representing part of the network and part of the computers. You're literally saying, I'm in the subnet of 0 and I have a computer of 5. Now if Albert were in the 128 network, I would turn on the 128 and we would write the number 133 in here. But what you're really telling the computer is I'm in a network of 128 plus I have a computer of 5. It'd be nice if we could just throw another period in there and write it that way, but we don't get that luxury. So that's kind of the strange part that people don't see in TCP/IP. It's like looking, it's not the mathematics, it's more of just seeing it. Kind of like those digital pictures within a picture. You got to stare at them for about 30 minutes and then presto, you see the picture. Okay, so going to the process, the 6-step approach, how many subnets do you need? Well, in this case, we're going to go for just 2 subnets. So it's 128, we turn it on, we got a 0 network and a 128 network. There's only 2 possible values. It's electricity, and every electric bit has 2 possible values, on or off. We may not count 0, like down here where it says 1. If we turn it off, it would simply be 0, but it's still a value. Okay, how many bits did you use to get to that? That's easy, 1 bit. We only turned 1 bit on. We got 2 networks out of 1 bit. So to make this a more meaningful example, let's use 4. Let's break up Albert's his office here to 4 networks and make it a little more complicated, because he doesn't, Alfred doesn't deserve a large office. He's going to stay in office 0, and we're going to have 64, 128, and 192. And so that you understand how we get to it, we're going to go through these 6 steps now. We already know that we're going to go to 4, so now that we need 4 networks, how many bits did we use to get to 4 networks? 2, 4. Networks push from the left to right, computers push from the right to the left. We're going with networks, so we're pushing to the right from 128 to 64, and we're doubling to 4. And here's your 4 possible values: 0, 64, 128, 192. Well, it's one thing to see it, but how do we get there? Well, question 3, question 4 will get to that. So first, what's your mask? That's an easy answer. We add up the 2 things that we turned on. 128 plus 64 equals 192. So there's our mask. Now we know the mask. Question 4. Looking at this template again of 128 through 1. 64 is our block size, and that is used for creating the subnets. It's always the lowest number in the mask, so it's real easy. Just pick the lowest number, there's your block size, and that's what you're going to use to create your subnets. And really all you're saying when you look at your block size, you're saying how many times will 64 go into 192? It's really just a division problem, but we need to see each one, so we do the long math. Alright, and here's another representation. We're talking about the host here, but this would show you how we came to the 4 offices. And Alfred's in office 0, and he gets to have 62 computers left over in that office. I just threw that up for visual representation. Now, 5, what are your subnets? Taking that picture from the last one, here's what we're doing. We're taking that block size. 0 is the first network, plus 64 equals 64. 64 plus 64 equals 128. So it's just simple addition. We're just incrementing using simple addition until we reach our mask. And so there's our 4 subnets. It's really that simple. So far we've gone through 5 of the 6 questions, and it's really not that hard. It's all real basic. The only real thing that people have problems with is understanding what this line is doing. That yes, this is the network side and this is the computer side. And then I'm going to write one number in that dotted decimal notation to represent the network and the computer. 6 is kind of a 2-part question, but I'm going to show you, since we're in the 4th octet, there's a nice little cheat you can use. How many hosts do you have? Well, 64 is your block size. It also happens to be the remaining number in that octet. So if you're in the 4th octet, this is real straightforward. 2, 4, 8, 16, 32.